Towers of Hanoi is one of my favorite kind of examples of recursive puzzle. Um, so, yeah, also called Benares Towers, Tower of Brahma, Lucas's Tower. We're going to go ahead. No, I don't even know what that is. Why did you suggest that as opposed to what I was trying to pull up?
Windows.
There we go. Okay. So, anyway. The Towers of Hanoi is this game that we play. It is basically a puzzle game, more of a puzzle, and it looks something like this. Here's a rather big one in Mexico City. It's actually rather impossibly big for the purpose of the puzzle, because an ideal solution, the minimum number of moves needed to solve the puzzle is 2 to the n minus 1, where n is the number of discs. So every disc basically doubles the number of steps you have to take to run it. So in case you're curious, right, what does that kind of runtime, right, if you were to implement an algorithm, which we will be doing, the runtime for solving Towers Hanoi would be, in this case, O of 2 to the nth to the nth power. It's exponential time. This is what we call exponential time. And your runtime is, not great, because every time you add a disk, you're going to double the runtime of this program. That's fine, though, in the cases where the solution is going to, where basically that's the best you can do for the solution. So what is this puzzle? What is the way that this works? And I sometimes bring in a little tiny disk to show, and there's a video recording of me doing this puzzle and the lecture recordings. So first off, the goal is to get all the disks from here to here, from the leftmost peg to the rightmost peg. And you might be going, Professor Rosen, that's not really that hard. All we have to do is just lift up all the pegs at once, drop them on the last peg, done in one move. I've solved the puzzle. Okay, so I guess we have to address the rules. Rules are you can only move one peg at a time. Sorry, one disk at a time. And you're like, well, that doesn't sound so hard, right? We toss one disk at a time into here, and now the pyramid's just going to be upside down. The disk pyramid's going to be upside down if we just keep moving them into the second peg. And then now this upside down, we just kind of flip them over and put them onto the left peg. Problem done, right? So we have one more move, which makes the entire thing actually worth being a puzzle, which is, and the thing that makes it worth being a puzzle is that you cannot put bigger disks on top of smaller disks. So as you'll see here, right, I move this disk over here, I cannot do this. I cannot drop it over here. And this is what makes it a worthwhile puzzle. You can't put bigger disks on top of smaller disks. You can do this, but as you'll see, that is not actually the moves we need to solve this puzzle. So the solution to this puzzle has a number of different solutions. There's an iterative solution, but I prefer a recursive solution. Now, if you think about it, how do we model each of these pegs, right? How do we model this problem? And the answer is we'll take each peg, and we model that as a stack, because you can only operate off the top of this, right? You can only move a disk off the stack and put it on top of the stack. So it's a stack of disks, and the pegs just kind of help hold that stack into place. So we will just create 3 stacks to help us with this. Make sense? And then we just have to make sure that as we move our pieces, we aren't violating any of the rules. We don't necessarily need to do if-else statements if we can figure out what the rules are and just do it appropriately. So the goal is to create a program that kind of shows move by move how this would work. So how do we solve this? Like I said, there's an iterative solution, but it may be easy to kind of see when you see my thought process on how to solve this. So the issue is that I need to move to get 3 disks over to here. I got to basically make sure that this bottom disk ends up over here before I can think about moving these 2 guys on top of it. which means I have to think about how do I move these top two disks out of the way. And we think about it in reverse, right? Okay, we can think about it kind of like this, right? We're going to start here, 1, 2, 3. And that needs to go to, and when we do that, that needs to transition into being something, not sure what it is, but then a 3 over here, right? And from there, and in order that, like the 1 and the 2 have to be somewhere. I'm not sure if it's going to be, and we can leave for the sake of, as we figure it out, where that's going to be. And then finally we can transition to having it empty, empty. And 1, 2, 3. So I'm breaking it up into subproblems. But if we think about it, we've kind of got the same subproblem, which is I got to move these 2 disks out of the way to move this single disk to where it needs to go. And then I can move those 2 disks on there. So in order to move 2 disks out of the way, well, we can actually think about where where 1 and 2 need to end up. In order for us to get to this scenario, right? We have to have the disks like this, right? So I have to get the disks 1 and 2 over to here, and then the 3 over here. And then that would mean that basically this is the move I make, kind of to get to the middle. So the problem is, if you think about it, I've got this stack, and what I need to do is I need to focus on moving these 2 disks out of the way, and then focus on how do I take those 2 disks and move them back on top. In other words, the question of how do I move a tower of size 3 becomes how do I move a tower of size 2? Make sense so far? So and if we think about it not too hard, to get into this configuration, what do I need to do? I need to move this disk out of the way, so I can put this here and this here. Now that's out of the way. This needs to end up on the bottom over here, so move it like so. 7 moves, right? Restart. Can't go down below 3. Let's talk about, so now we can kind of think about this in terms of how do we do 4. To move 4 disks, we have to move 3 disks, a tower of size 3 out of the way, right? To get to move a tower of size 4 over to here, our first step is we need to move a tower of size 3 out of the way onto the middle disk. In order to do that, to move a tower of size 3, we got to move a tower of size 2 over here, which means move a tower of size 1 over here, size 2 over there, size 3. And this is where it kind of starts looking weird, right? So notice that it took 7 moves to do that because that's the minimum number of moves you need for a tower of size 3. Now we can move this guy out of the way. Now we got to move this over to here. The bottom disk is going to go over here, which means we need to move a size 2 tower over to here, which means move this over here. Now we've moved a tower of size 2. Now we move the tower of size 2 back on. Make sense? So what it becomes with 5 is you're going to move a tower of size 4. To move a tower of size 5 over to here on the left, move the tower of size 4 to the middle, okay? Which means moving a tower of size 3 over here, which means moving a tower of size 2 over here. Tower of size 2. Now we can finish moving a tower of size 3, which means now we can start moving this over here, the tower of size 3. So we need to put this disk over to here, we have to move a tower of size 2 over here, right? It gets a bit brain bendy after a while. You just have to remember, okay, where am I moving tower size? If I need to move this tower, what is the current size of the tower I need to work on? And then reducing that. Then this becomes tower size 4 moving over to here. Moving a tower size 4 means moving a tower size 3 over to the left, which means moving a tower size 2 over to here, which means moving a tower size 1 over here. and we clear off that space. Okay, and now we need to move this over to here to complete the tower size 3. All right, and now move tower size 3 over to here, which means we want to move the tower size 2 to the middle, which means move this over to here, and tower size 1. And that's it. That's a tower size 5. It starts getting really ridiculous once we get to 6, but the same principles hold for however many disks there are. To solve size 8, you're moving a size 7 over here, and to move size 7, you're moving 6. To solve a tower of size 6, you're moving the subproblem of moving 5 and 4 and 3. This is a recursive puzzle, and we kind of ignore the bottommost disks as we go down with subproblems because we treat that as part of the floor. This graphic on Wikipedia is actually amazing. It's a scalable vector graphic that you can click on, and it shows, oh, here's the tower of size 4 we're trying to move. Let's click on the sub-steps for that. And it shows you. You move the tower of size 3 out of the way, then you move the bottom disk, then you move the tower of size 2. Each of these are the recursive steps. Right? These are just simply the subproblems for it, and that you can unfold as need be. So that's a really good thing to click through if you didn't really fully grasp that. There are fun variations of this. Okay, fun variations does it not have the fun variations? Oh, yeah, it does. Like this one, the bicolor Towers of Hanoi, which starts like this. You've got your white and black discs, same rules, but you want to end up with like this. Right? There's all sorts of, anytime there's a puzzle, there's a variation on it. It shows up in tons of different things in culture and stuff like that. Yep. Genshin. It shows up in Genshin Impact and the Quest apparently. Let's see, where is it? I know there's one in.
It's in Mass Effect.
I think it shows up in Stellaris as well. It shows up every so often. It's a fun little puzzle. And you can see a lot of it sometimes at science museums and the like. It's fun. And does it still have the algorithm over here? It used to have the algorithm over here. That's okay though, because we're just gonna write this. Okay. So let's go ahead and write the pseudocode for this. And your job today is to translate this into Java. I've got a Dropbox called Towers of Hanoi. On the or Towers in Class exercise. That's where you're going to upload it. Okay, and your job today is to translate this pseudocode into Java. Okay, so what we're going to do is that we are going to declare that we need we're going to solve. Let's see. We're going to do the number first, right? We're trying to solve moving a tower. We're going to call this move actually. Move n disks from source to destination, and we're going to call this temp, right? So we're always going to move from the source to the destination, and this third one, and this is whatever peg is not the source or the destination, because it's going to be, that's where we're going to move a bunch of stuff out of the way to. Okay, let's see. We are going to do, and so the way this is going to work is that. This is kind of, I'm just writing down the algorithm I was using, right? Which is, what do I need to do? I need to move, in order to move 5 disks, 5 disks over to here, say n was 5, I'd have to move 4 disks out of the way. So in order to move from source to destination, this would be temp. I move 4 disks to temp. So let's go ahead and make an if statement. If, say, n is greater than or equal to, if n is greater than 0, as long as there's disks to actually move, right? What do we need to do? We are going to move n minus 1 disks, right, from source, and we're not going to go from source to destination. We're going to go from source to temp. right? N minus 1 disk out of the way. Then we are going to say source dot add. We're going to go ahead, actually push. Not source dot push. Destination dot push source dot pop, because these are stacks, right? Move from n-1 source to temp, and oh right, I have to throw in the third argument, destination over here. Source to temp. The destination is now going to serve as our temporary place to store stuff as we move stuff out of the way. So we're going to move if we've got 5, we're going to move 4 out of the way onto temp. Then we're going to move the bottommost disk, our current bottommost disk. And then we're going to move those 4 that we moved out of the way onto temp to back onto destination, and now source is going to be the auxiliary. Make sense? And then what we're going to need to do is, I think I'm going to make a separate function called print status, just to make it a bit more clear, because this is where a lot of students mess up. Because if I were to try to print source temp destination, they would swap around every single time, right? The order in which you were printing stuff. So we're going to basically call nothing. It's never going to be past anything. It's always going to print the same thing. And print status will be a function that looks like this. Print A, print B, print C, where each of those exist outside of the function. All right. So, and believe it or not, that's it. That's all. This is solve. Okay, and we just simply need to declare that A is a list, like this is 3, 2, 1, right? B starts as an empty peg, C is an empty peg. This is obviously just pseudocode and not a functional program. Save, desktop, towers.py, and build, execute, solve is not defined, right, called it move. All right. And now it's a functional Python program, because Python is just pseudocode with attitude, I guess. So there you go. And so now we see what the commands are. We move the little peg off, the little disk off, then we move 2, right? Then we move the smallest peg back onto 2, so everything's out of the way now. And we're ready to move 3, the bottom peg of the 3 stack, and then we do the steps of moving this on. This is it. And it works for any arbitrary size. I'm going to go ahead and do, in Java, this, so just FYI, in Java, these would be static variables, right? And this would be, and in Java, this would be in main. Because in Java, static variables are basically the closest thing you have to being able to use global variables. So that's, and we need that because otherwise we're never going to print these 3 stacks in the same order, and then that's going to be a headache. Make sense? So, so those would go elsewhere, but this should be fairly straightforward to translate into Java. Into Java. Now, a couple of keys here. In fact, you could probably ask ChatGPT to do it. Now, a couple of And that's one of the favorite things I love using ChatGPT for, which is to translate one thing from one language to another. Now, a couple things to note over here that in case you don't know Python, right? The way Python works is that stacks are just lists, because why not? And this is, in the back of the list is considered to be the top of the stack. And so pop removes the last thing in the list, and append pushes it onto the back of, it's adding, this is the add function in Java. So your goal is to translate this into Java, essentially. And it's, again, it's not really a particularly, the reason I like this is because this looks like pseudocode. Your Java code is going to look like pseudocode, because you're like, there's no way it's that simple, because we have all these complicated moves. But the complicated moves essentially are just moving one disk at a time. This is necessary because this is basically, what if it's our recursive case? Our base case is we're not going to move any disks, essentially. We could easily just simply say, if n is equal to 1, move source to destination, and just that be that. But and that could be our base case. But it's so much cleaner if I just write it if like this, and let the base case say, oh, if we get past a 0, just don't do anything. All right. That's what I have, and I'll also go around and then help you with your maze homework, as well as getting set up with your recursion homework. Again, the recursion homework is meant to be a lot of fun, so I hope you take the opportunity to do that. That being said, I have the full expectation that you are planning on working throughout all of spring break, and that's your intention, and then it will become Sunday at the end of spring break and realize, oh yeah, I didn't do anything for my classes. And that is what I fully predict you will do, because that is what everybody does. Mm-hmm. So, long story short, if you can work on this during spring break, on your homework during spring break, awesome. It will help you, stay fresh during spring break and not be as rough of a transition. But if you don't do it, I fully understand.
Exactly. No, I'm hearing on that one.
It's supposed to be your break, right?
Yeah. If you got nothing to do over your spring break, you can touch base on this.
If you are behind, I definitely recommend using spring break as that time to catch up for any of your classes.